Welcome everybody to this SP technical lectures that close the uh, program of this year. We'll start again on September with address lectures and distinguished lectures and a very dense program. This last lectures, I think, is a very interesting lecture dedicated to stimulation technology. Stimulation technology is a very hot topic nowadays. It's a very successful way to improve production and also reserves at the end, as is one of the key factors for the success of shale gas development. And now is also a hot topic because there starts a long debate about environmental impact and many other things related to stimulation. So it's very and have very hot topics, and we are very happy to have this lectures as the Italian section of SPE. The lecturer today is Joseph Hayub, and he is the protection and completion engineer discipline manager with Schlumberger, with a very long career in stimulation technologies. Joseph is probably one of the key persons that launched the frac impact technique in the Gulf of Mexico and have 12 patents and 35 papers on mainly on well performance and testing hydraulic factorings and many other items relating to stimulation technology. He was also a distinguished lecturer 2 times with SPE, and is also director of the technical DNC of SPE International, so as serves as volunteer of SPE many times, and this is another thing that makes us very proud to have Joseph here, because as a volunteer of SPE that gives a lot of time, a lot of energy to SPE. I encourage all of you to do as well your contribution to SPE Italian section. Become a volunteer because taking part of our initiatives and propose many possible lectures or other parts of the program. But now leave the floor to Joseph. Thank you, Joseph, for the lectures. The title of the lecture is Stimulation Technologies, Deep, Broad, and Successful. Thank you.
Thank you, Eduardo. I would like first to thank you and the SPE local section in Italy for their kind invitation. I'm very happy to be here in Iran. And as you mentioned, volunteering is really the blood of our organization. That's how we all share our technical knowledge and interact with each other as members of the same society. So today I would like to illustrate the depth and breadth of stimulation. As you probably know, stimulation is generally a very successful technique. So those among you who work in stimulation should feel very proud. And those who do not work in stimulation, my message is that we need you. Your input and collaboration are crucial to help unlock the full potential of stimulation. So we'll start by illustrating how successful stimulation is, looking at performance following stimulation treatment. And the economics of stimulation, at a very simple level. Then we'll take a look at the depth of stimulation technology. We'll look at some new technology development and the different areas, if you work in stimulation, you could be interested in. And then we'll take a look at the breadth of stimulation, at the necessity of integration and close interaction with the other disciplines to help make stimulation reach its full potential, if you want. And we will conclude, and I'll take question answer after that. So As you know, well stimulation accelerates recovery because it improves the production. You acidize the well or you hydraulically fracture the well, and the production will increase. But it also increases reserve, and basically it's sufficient to think of all the oil and gas that would not be produced if we didn't have hydraulic fracturing. So the definition of reserve is what we can economically extract, and hydraulic fracturing is a key enabler to help develop and extract tight gas, shale gas now, and others, improving the life of the well in other areas as well. In any case, it impacts the profitability of field development, and basically that's what I would like to illustrate very quickly, very simply, how rapidly stimulation recovers its cost, right, without going into complicated calculation of IRR or return on investment or things a little more sophisticated than recovering the cost. So this is the first example from the Gulf Coast of Mexico. And this graph is basically a classic nodal analysis graph where you have the bottom hole pressure on the y-axis and the production rate on the x-axis. The well was produced, this well was gravel packed, as they do with most of the well in the Gulf Coast, and it was producing at 1630 psi wellhead pressure and making 1200 barrels per day. And on this graph, basically, you see this line is the inflow performance relationship. It's the capability of the reservoir to deliver fluid to the wellbore. Fluid moves from high pressure to low pressure. So those among you who are not familiar with nodal analysis can see that in order for the fluid to come from the reservoir to the wellbore, the higher the rate, the lower the flowing pressure in the wellbore to attract more fluid coming from the reservoir. So this is the reservoir performance curve, or IPR, it's called the inflow performance. And this curve is the tubing intake curve. Basically, you imagine that there is a pump at the bottom of the tubing, and you're pumping rate up the tubing. So if you want to send higher rate up the tubing, you need to overcome not only the hydrostatic weight of the column, but also the friction. So with higher rate, you have higher friction. That's why this curve is moving up. And if you want to know why this one comes down, you can ask me about it at the end of the talk. But at the intersection of these two, because the system is the reservoir and wellbore, including the tubing, is where the production is, right? Because you at the flowing bottom hole pressure has to be the same that the reservoir sees and that the tubing will see as well, and the rate as well, right? So if you look at this, and there was a build-up test done on this well showing the KH, the permeability was about 500 millidarcy, and the skin in this case was 210. But for 500 millidarcy, a skin of 210 basically is about, if you look here at the pressure drop from here to here, that's your delta P due to skin, basically. And it's about what, 500, maybe about 700-800 psi, right? So high numbers of skin don't, give you lower delta P in higher permeability reservoirs. Skin is basically just a dimensionless pressure drop. So if we remove that skin, theoretically, and go to a situation where there is no damage near the wellbore, a skin of 0, basically your production rate can go all the way up to here. So in this particular case, this well was acidized. It was determined that the issue was damaged by clay from drilling mud and so on, and it was acidized using mud acid treatment. As you know, mud acid is a combination of HCl and HF, and there is a whole procedure, with pre-flush and so on. I won't go through the detail. And at the end, it was tested again. It was producing about 5,000 some barrels per day, but at a higher wellhead pressure, 1860. So we can match that again by looking at the IPR of the reservoir with a skin of 15 now, and the tubing intake curve at the wellhead pressure of 1860. As you can see, for a higher wellhead pressure, your bottom hole flowing pressure will be higher as well. So that's why your tubing intake curve moves up. So we still have a skin of 15. We didn't remove all the damage, but part of that skin of 15 was due to partial completion because they perforated only the top part of the reservoir and left the bottom part not perforated because they were afraid of water coming out from another zone below. So basically, if we lower the wellhead pressure by opening the choke on surface, we can go back to the 1630 psi, and our production rate will be here, close to 7,000 barrels per day. So if we look at the increment, 7,000 minus 1,200, that's 5,800. Let's say round number, 5,000 barrels per day extra. If you multiply that, even how many dollars per barrel you want to use? 10, that gives you 50,000, right? $100 is 500, so 250,000 if you use $50. The cost of the acid treatment with the boat, this was offshore, could be around $250,000, $300,000. So it will pay for itself in a day or less than a day, basically, right? Let's go to the next example. This is a gas well in East Europe. And this well was producing about, and this one, I think you like the units here more because you use the SI units as opposed to oil field in Italy, right? Or not? You use cubic meters or use barrels per day? Use both? Okay. So this one, it was producing about 30, I think about 32 cubic meter or so. And at 69 bar wellhead pressure, right? And the permeability of this reservoir was tight in the range of the milli-Darcy. So we matched the production with the same IPR cubic intake curve here. And if we remove the skin of 29 of the current situation to 0, we produce this much more, around 250. But if we hydraulically fractured the well because it has low permeability, we can even improve the production further and get close to 650 or so thousand cubic meters per day, right? So this one was hydraulically fractured and tested after the treatment, and you see the production after the treatment went up to close to, I guess, about 100 cubic meters. 100,000 cubic meters, per day, but at the wellhead pressure of 306 bars. In this particular case, the separator they had could not handle higher rates, so they couldn't open the choke and lower the wellhead pressure. But if you are able to handle the high rate, you will have much higher production here, and if you do the difference in gas production and use $1 or $2 per 1,000 standard cubic feet per day. I don't know what the price is in Europe per 1,000 cubic meters per day. But anyway, if you use like $1 or $2 per MCF, which is 1,000 standard cubic foot per day, and look at the incremental increase, you will estimate about 2-3 weeks of production will pay for the treatment. Right? The treatment, let's say, was about $450,000 or something like that. Now, this is another example. This one is from West Africa. It's a Nigeria well, and it was producing about 90% water cut. So this is an old reservoir, water flooded. And you see the production decline in here. Then it was determined that it was due to fines migration, and it was treated with fluoroboric acid, which stabilizes the fines basically and stimulates the production. And you see the production went up, let's assume it went up to 2,500 barrels per day of liquid. And initially, let's say it was 500, just to simplify things, so it's 2,000 barrel liquid per day additional. If 10% of that is oil, that's 200 barrel oil per day. Again, if you use, $50 per barrel, what's the net do? That's $100,000. 10,000. So $10,000 per day, and let's say the treatment costs 200,000, so it's 20 days or a month time basically before the treatment pays out. So the reason I'm showing you these examples is to try to classify a little bit the candidates. So you can basically you look at these criteria, right? You look at the candidate well. If it's good, meaning if you determine that it will benefit from a stimulation treatment. How you determine that it will benefit from stimulation treatment? By doing this nodal analysis, typically well performance of the well. And if you don't have all the data needed, you may need to have a well test to know what the KH of the KH overview, the variability thickness over viscosity of the reservoir is, and the pressure, and so on. So if the well is a good candidate and the reservoir is good, what's a good reservoir? Good reservoir meaning good permeability, good pressure, at least hydrostatic, not depleted, and no water cut, it's not flooded and high water cut. So in these cases, the payback time of the stimulation treatment is days to weeks maximum. Right? It pays back very quickly, meaning any other economic indicator will look great. If the candidate well is good, but the reservoir is poor or old, what's poor or old? Poor reservoir meaning very tight permeability, low permeability tight, like tight gas, or like the shale, for example. And I say old because old reservoirs typically they are water flooded, you have high water cut and so on. So in these cases, the payback time could be weeks to months. It could go several months, but it's still very good. There is no investment that pay itself back that quickly, and then you start making profit over it. Now, if the candidate well is bad, meaning the well has other issues that will not benefit, it will not benefit from stimulation treatment in increased production, or you have mechanical issues in the well, you can pump in it with pressure, or you can put acid in there, whatever. So if the well candidate is bad, then you do not stimulate because you're not going to get any benefit from it. And the key to a success stimulation is to be able to select the good candidate and apply the correct technique. But generally, most of the time, it works because most of the time, a lot of the wells are good candidates. But you have to look out for the other ones. So let's move on to the next part. I said initially that I'll illustrate the success of stimulation. Then we're going to talk about the depth of the stimulation technology. And I'll illustrate that with some examples from hydraulic fracturing technology and some from matrix treatment. We are also some advances in the interpretation of the different measurement done during stimulation. I probably won't have time to go through that, but the interpretation part, but if you have a question, we can talk about it at the end. So if you look, for example, at the evolution of fracture conductivity, which is the product of the permeability of the propellant inside the fracture by the width of the fracture over time, you see that we managed as an industry to increase the conductivity of the hydraulic fracture treatment by changing the fluid technology, lowering gel loading, using some polymer-free fluids, increasing the breakers, oxidizers by encapsulating the breakers. We were able to load the fluid with breakers without compromising its integrity too early before you finish the pumping treatment. And that will allow the gel, the viscous fluid that was used to transport the propellant to break and become less viscous so it cleans up easily when you finish the fracturing treatment. And using different propellant sizes, like for example in crack impact treatment, we started using 4060 mesh, and then we realized that which was the rule dictated for sand control initially. And then we realized that when we do frac and pack, we can use one size higher than that without any sand control issues. And we moved to one size higher to increase the conductivity of the fracture, which is critical in the case of frac and pack. Right? So we managed to increase that, but we still, most of the time, because of the residue from the polymer and etc., we still recover about maybe 50% at best of the full conductivity of the fracture. So recently, in the last few years, Another technique was introduced where instead of placing the proppant everywhere, try to make a homogeneous placement of the proppant everywhere in the fracture, we try to design the treatment so that the proppant is heterogeneously placed, leaving some small space between the different proppant slugs. And that space basically will be create like almost an infinite conductivity for the fluid coming toward the wellbore, right? And increase the conductivity of the teeth in the mouth. Another development in modeling, and that was really spurred by the naturally fractured nature of some of the shale reservoirs where you can apply this, is initially, as you may know, hydraulic fracturing models assume a planar feature, only one plane of fracture that intersects the well and goes into the reservoir, and it goes in the direction of maximum principal stress. Basically, the fracture propagates orthogonal to the minimum in situ stress because that's the easiest path for it to open and propagate. Now, in naturally fractured reservoir, when you initiate a fracture, it will intersect many natural fractures. And a model that was developed in the recent past, in the last 2-3 years basically, is a model that allows the hydraulic fracture or allow us to model the interaction of the hydraulic fracture with all these natural fractures, right? And take into account, the stress shadow effect from the other fractures and so on. I'll illustrate here a little bit what could happen. This is a wellbore, and this is a fracture propagating as a planar feature. It could be stopped by a natural fracture. If it's a natural fracture, it's cemented and really hard. You don't cross it. Or you could cross a natural fracture, or you could, propagate along the natural fracture and then open, more fractures propagating from it. So there was some theoretical as well as experimental work done to understand the different conditions under which you have blunting, crossing, or what we call here dilation or activation. And a model was built to basically allow the modeler to try to match a little bit what we see during a fracturing treatment from microseismic events, right? So this represents like a horizontal well here, and these dots are the events recorded during microseismic monitoring during the hydraulic fracture treatment. And they've done here, I think, 2 or 3 stages. And this is what the unconventional hydraulic fracture model basically is giving us. And if you use the conventional model, it will propagate only one planar feature here, and the net pressure from it will be much less than what was measured in reality. If you use the unconventional model, because of the interaction with these natural fractures and the way these fractures propagate, the resulting net pressure from the model matches better what we observe in reality during the treatment. Okay. Actually, if you have any questions, since you are with me in the audience, feel free to interrupt me during the talk. I don't mind that. Now, this is a experimental work. So we talked about modeling work before, and we talked about some new propagation or new design technique for hydraulic fracturing. This is experimental work just to see how the fracture propagates in soft sands, in unconsolidated sands. So what you're looking at here basically is a block of soft sand after we did the hydraulic fracturing treatment and we removed the box from around it. And this here is the looking top down from the top of the box. The side of the box are still there. This is the pack of sand that we packed inside the box. This tube here represents the well, and there was some perforations at the bottom, and you see the fracture that we created in that sand experimentally by pumping fluid inside the tube here with a fracturing fluid that had a it's a kind of glue in it basically, so that we can glue the sand where the fracture propagated and can see the features. So you see the top of the fracture here, and here it's the same with another angle of the picture. This is from the outside of the tube after we remove the side, and you see the top of the fracture here that we see here, right? And here basically we are removing the excess sand just to be able to see where the fracture propagated, what shape it has. Again, removing more sand, you see the fracture, where the fluid and the glue went to glue things together. It's a kind of small amount of epoxy added to the fracture fluid, basically. And here again, we're cleaning it, and this is the final shape of where the hydraulic fracture fluid went. So it's mostly planar, but with some more complexity, on it. But I would say it's mostly planar, for these alkoxylated sands. So the reason we are doing this experiment is try to understand how fracture propagates in unconsolidated sand, because hydraulic fracturing was developed for brittle hard rocks, and there was always a question mark about how does it propagate in unconsolidated sand. Because it's a bit different. The height of growth will be different, the width will be different, and so on. So moving to another topic. So here I just want to illustrate the depth of the stimulation technology. We looked at design, we looked at experimental work, right? We looked at modeling work with the unconventional fracture model. Here we look again at another experimental work that is done for understanding acidizing carbonates, and development of wormholes. So take here, it's a linear core where you flow acid from one end and out the other end. And you have pressure sensors basically along the core to measure the pressure. And as we pump acid through this, at a certain rate, we have the best conditions to propagate the wormhole. It depends on what is called the Dam-Collar number. And in this case, we are pumping what we call a self-diverting acid. The self-diverting acid, the way it works is that as the acid goes in thin, regular viscosity, and as it expands and the pH rises, it becomes viscous and thick. And then as it spends completely, it re-thins again. So as you see here, we are monitoring each color here correspond to the pressure record of the same color on the graph, right? So the blue is monitoring the pressure difference between these 2 points. The pink is monitoring the pressure difference between these two, and so on. So as we pump the acid, basically acid arrives at the core phase. You have some rise in the pressure in the first one, and then it drops. Then the next one rises because self-diverting acid is viscosifying in this area, making the pressure drop higher. And then it drops down as the acid spends completely, and the wormhole basically bypasses this section, and so on. So the model from that is basically that you have zone of high permeability where you have basically stimulation and wormhole creation here, so there is not much pressure drop. A zone of resistance where the acid is arriving fresh there and expanding, the pH is rising, becoming viscous. And then a zone of spent acid filtrate that is ahead of it, and then the zone at initial conditions, right? So this allows us to build models of these acid in carbonate and predict a little bit how the acid will go in different layers based on the permeabilities of these layers and the propagation of wormholes and so on, right? So we covered, if you like, the success of stimulation. We covered the depth, looking at examples, whether they are experimental, modeling, or design of treatment. Last, I wanted to cover how broad and the need to integrate with other disciplines. That need is crucial in stimulation, right? So when you stimulate a reservoir, you have to be able to know that it is a good candidate, that it will benefit from stimulation. So you need reservoir information, like we saw about pH over mu, pressure of the reservoir, how many layers, to be able to get a good IPR, inflow performance relationship, the performance of the reservoir. And if the correct treatment is hydraulic fracturing, you need also to know a lot about the geomechanics of the reservoir, the stress profile vertically, and also the stress orientation, so you know where your fracture is going to go. So you need to determine what are the three principal stress direction, what is the stress magnitude, and the type of rock. So in particular, for example, in shale, you need to see, is it ductile shale or is it more a brittle shale, based on the mechanical properties of that particular rock. So geomechanics is important, but also, we use, as I show you one of the example, microseismic monitoring, where you basically put geophones in a nearby well, and you listen to the passive microseismic that happens or you listen passively to the microseismic event that happened during the hydraulic fracturing treatment. And you try to locate where these microseismic events are, because likely they will be concentrated somewhere close to where the hydraulic fracturing is going. Right? It doesn't necessarily mean that where there's microseismic event, there is a fluid that arrived there. It means that the fact of fracturing created a stress condition there that made the rock slip. Right? And okay, so we need all of these disciplines. We also need petrophysics, because you need to know where the hydrocarbon is, right? To be able to stimulate and put your fracture in the correct zone, not somewhere outside where the hydrocarbon is. I will illustrate, that with a couple of examples. So fracturing design in the 80s used to be very simplistic. The fracturing engineer used to go and ask the reservoir engineer, what is the reservoir height here? Okay, and give me the reservoir height and what the permeability is. And then they run a 2D frac model. They assume the fracture height is going to be fixed. It will be either the reservoir height or a little bit long, higher than that. And then that is fixed, and they use what we call a 2D fracture model to propagate a fracture that looks rectangular in shape, basically, with a fixed height. Nowadays, if you want to do hydraulic fracturing treatment, you need to look at all the petrophysical data. You need to look at the rock mechanical properties, right, that like we saw before. You need to look at the reservoir properties, that not just get a K, permeability, and a height. And in the case of the unconventional reservoir, you need, in addition, some realization of the discrete fracture network if you want to use unconventional model with interaction with the discrete fracture. So it's getting much more involved and much more complicated, I guess, but it's needing input from all the other disciplines if you want to include all the complexities that are in the reservoir. This is an example of integration. Okay, maybe I'll try to do this interactively with you here. So this is a classic build-up test analysis, right? So this is a log-log graph with the pressure change and derivative on the y-axis, and elapsed time or shut-in time on the x-axis. This is the pressure change versus time, and this is the derivative of the pressure. Those who are versed in well test interpretation, you know that wellbore storage, which is the effect of compression and decompression of fluid in the wellbore, appears as a unit slope straight line. And then we recover from that, and if we see here a flat derivative, that corresponds to the straight line of the Horner graph. It's the slope of the Horner graph, basically. It becomes constant because you're on a straight line. So we use this part to calculate KH over mu. And this is typical behavior, this pattern between the pressure change and derivative is a typical behavior for a homogeneous reservoir with wellbore storage and slightly stimulated. If it was very high skin, you'd see the derivative doing a hump like this, and the pressure change would be higher here, and the derivative would do something like that. So we calculate a skin of minus 1.3, slightly stimulated, a perm of 2 millidarcy, very, I mean, it's slow, but it's not too bad. So they first came to me with this interpretation saying, a consultant analyzed this well test. This is what we gave as results. The well was hydraulically fractured before the well test. And based on the hydraulic fracture, they placed like 500,000 pounds of proppant in there, 500,000 pounds. The skin of minus 1.3, if you estimate what is the fracture that is due to just the skin of minus 1.3, you get something like a couple of feet, right? And you don't see here the typical signature of fracture in the well, because if you see that, you will see half a slope here, both on the pressure change and on the derivatives before you get into regular flow. We don't see that typical signature of fracture. So the operator was getting a little bit upset and suspicious, saying, did we really put 500,000 pounds of proppant here? Because you can't fit it all in a couple of feet of fracture. Or did we just turn the pump and moved the proppant away, brought it in trucks and took it away after the job is finished? So what do you do in a situation like that? I ask for more information, right? This is just one piece of the information. So you ask, okay, can we see the log data on the reservoir? Do you have any other data? As it turned out, they had a lot of data on the reservoir, right? So if you look at the logs, they already knew that they had two different zones, and they took cores from each zone, right? So the top zone was a conglomerate, and if you look at the piece of core, you could see pebbles basically in it. It's really conglomerate. Right? And they did rock mechanical testing on these cores. So on the conglomerate, they found that the Young modulus is 10 million psi, right? And the perm was 4 or 5 millidarcy or so. And the 4 or 5 millidarcy was done from DST. They did the DST on the top zone and calculated the perm. The height is from the log data, about 35 feet. This one, they took also a core from it. The Young modulus was 6 million. And the height from the logs was about 70 feet. They tried to do a DST on this zone, drill stem test. You know what drill stem test is, right? But they didn't flow. The well didn't flow, so it must have had very, very low probability. So when this well test was analyzed here, the assumption is one layer, homogeneous reservoir, one layer, and that's what we got. But the reality, if you look at the petrophysics, the logs, and then the core data, is that we have two very different layers. And if I'm the fracture design engineer and I look at this, even without running models, usually the fracture will try to propagate and take in the easiest path, the path that will spend the least energy. So the easiest path for a fracture is the thicker zone, the lower Young modulus zone, right? Because the Young modulus makes the rock very stiff. So it's less stiff, it will be able to crack it easier. So if you look at these, which zone you think your fracture will tend to propagate in, preferentially? And also the zone that will have the least leak off, because if you use all your fluid, if you have high permeability and your fluid leaks off into the reservoir, you can't have enough energy to propagate. So looking at these three criteria, where do you think the fracture will go? Yeah, probably it will grow here, right? Not so much in the conglomerate. Now, if I go back to my well test and say, I don't want to analyze my well test as a simplest model, which is one layer homogeneous. I want to take into account that I have two layers and two fracs of different lengths. So I have one big frac here probably and one small here. And analyze the well test, look what happens. So I'm analyzing, the model is the continuous line here, right? And the data is the dot. So if I analyze the well test using 2 layers, now I find a perfectly good match, as good as the prior one, but with 1 layer saying I have 4 millidarcy and 9 feet of fracture, and another one with very low probability and 460 feet of fracture. Now I can at least have coherence between my well test interpretation and my fracture placement analysis. Both of them are given the same answer, right? So the reason I show you this is that this integration across discipline is important, especially when you are doing interpretation, right? So if you do interpretation of well test or even interpretation of placement of fractures or interpretation of the geology or geophysics, there is always more than one possible interpretation. Because interpretation, basically, you look at the system that is unknown, and you're analyzing an input signal and the resulting output signal. So in a well test, the input signal is a rate of change, and the output signal is a pressure change. In seismic, you send a wave, and then you get the reflection back, right? And you measure that. In logging, is the same, right? You create a differential of potential, and you measure the resistivity or the current. Or in acoustic, you have a emitter and a receiver, whether it's acoustic or electromagnetic or other, right? And you try to analyze these input and output measurements and infer from them what system you have and what are the properties of that system. And as you've seen in the well test, for example, there could be different systems with different properties that for the same input signal give you the same output signal. And the smarter we get in any particular discipline, the more alternative models or alternative interpretation we can find. So, for example, here I illustrate, just for illustration, that let's say we have a well test and we could analyze the data in 3 different ways, and the fracture placement in 2 different models, and the logs. In logs we have resistivity, we have acoustic, we have nuclear logging, etc. So let's say we have only 1 model in this case, but you could have multiple, right? Geology or physics as well. So the idea is that you need to look at each one of these interpretations and see which ones are consistent together. So for example, this one in well testing is consistent with this one, but not consistent with what the logs and geology is saying, then it's not a good representation. So you have to find one that is consistent across the board, where the geology, the logs, the fracture placement analysis, the well test analysis are all coherent, that they correspond to the same image of the reservoir. And then you can say, okay, I think I have a picture that is more likely to represent the reality that we have down there, since we can send anybody down there to look at it, right? So this is the main message. It's referenced as well. I published that in SPE production facilities around there. Which brings us to the conclusion. Basically, what we covered here is, I illustrated how simulation technology is broad. That we really need this integration. We need to establish that dialogue with the other disciplines. Deep and successful, right? It does provide challenging and fulfilling career for people interested in doing stimulation, whether they like to do research, we saw some research example, whether they like to do field applications, again. And it has significant interaction with colleagues from other disciplines and within the stimulation community. That concludes my talk. I'd be happy to address any questions or issues you'd like to discuss. Thank you all. Sure. Take the microphone, I think, just in case other people want to hear.
As in the presentation.
Let's see
as in the presentation, we saw that
we can get this on
we
your
saw the graphs from Nigeria, East Europe, and US.
Yeah.
So, I mean, just wanted to know the production rate increased after the stimulation. So, how long it sustained? It was sustainable in long term.
It depends on the cases. Where the stimulation is successful, it is sustained. So I remember a case for frac and pack, for example, where the first frac and pack was, well, not the very first, but one of the early ones that we did for Pennzoil. The problem was that they had gravel pack wells, and then the production declines. They acidize it, the production goes up, and then declines again. It's typical behavior of fines migration coming plugging gravel pack. So the decision was made at the time, and that was at the time where we didn't frac offshore. So it was a courageous decision by the operator to go and do frac and pack and try it. So we took the next two wells and we did frac and pack on them. And the idea then was that when we create a fracture and then a gravel pack, the velocities of the reservoir fluid coming toward the wellbore will be smaller near the wellbore because now it's distributed all the way around the fracture, coming through the fracture to the wellbore rather than coming all the way radially to the wellbore. And that should alleviate the fines migration. And it did because they monitored the production for 5 years afterwards and it stayed stable. They didn't have the same as they had before where the production would stimulate goes up and then decline again. So it's sustained, but you're always going to have some depletion relative to the reservoir unless you're doing pressure support, right? And if you're doing pressure support, at some point, water is gonna come. Now, tight reservoirs that are hydraulically fractured, will start with a very high production and then it will decline, right? It will decline depending a little bit on the size of the fracture, the conductivity, but mainly on as well the permeability of the reservoir. But you can predict that in the model, right? When you do your design of the stimulation treatment, if you know your reservoir parameter, you design the optimum fracture length based on whatever economic indicator you're using, and you can predict how the decline will happen.
Any other question? Question from webinar?
In your conclusion, you talk about a lot of research opportunities. What do you think about the place of nanotechnologies in this kind of
Well, there is a lot of interest in nanotechnology, right? There is a consortium actually now that looks at that with many industry partners, and they are looking at using nanotechnology for like EOR application, where you can maybe limit the amount of surfactant you have to pump by having it carried by other nanoparticles if it turns out to be cheaper, right? There are even discussion of having like nanobots, okay, but that you can pump in the formation to do certain things, but that's still way down the road. One idea, actually patented that a while back, is less ambitious when going to nano, just going to micro, meaning millimeter scale sensors that you can pump with the fracture treatment, for example. And but there are challenges in terms of signal transmission in the medium that is dissipated medium, it's saline water. Right? So there are challenges in how easy you can propagate the signal between the different sensors so they can talk to each other. The idea was to use like wireless sensor networks. Right? So you can use these type of technologies, if you like, in the future, maybe for Bremen mud, maybe in hydraulic fracturing, if we figure out a way to boost signal transmission enough to where they can connect with each other. But it's research, basically. It's nothing that will be available tomorrow, right? You have power issues, signal transmission issues that you have to resolve, but we're getting there. I mean, you see some sensors being built now that are very small, millimeter scale, that integrate a sensor, it integrates power, with small battery and transmission capability. But these work nice in air, right? Where you don't have the same dissipative issues that you would have in saline water. But people are thinking about nanotechnology to be used also as process.
Thank you. Any other question? No. So thank you so much for the
Pleasure. Thank you all.
speech. A small gift from Ask the Italian section.
Oh, thank you.
Best of Italy. Book not so huge, so not so easy
To carry.
Yeah, to carry to listen. So thank you again, and thank you all for attending this last lectures. So see you in September with the new Italian section program, and have you a great vacation period in summer, and see you again in September. Thank you all.
Thank you all.